Today's session is going to be on exploratory data analysis using Python. So what is exploratory data analysis? Exploratory data analysis is a set of tools and techniques that are used by data scientists to analyze and investigate data sets and summarize their main characteristics. It is not only used by data scientists, it is also used by machine learning professionals, deep learning professionals. It is used extensively in all areas of data science, business analytics, functional analytics, machine learning, deep learning, etc. Across the gamut of such technologies and such spaces, data science is used. Exploratory data analysis is used quite extensively. Now, what it does is that it uses very different kinds of tools and techniques with a goal, with varied goals. I mean, depending on the problem that you are solving, it can be functional analysis that you are doing with no intention of predictive modeling or machine learning modeling, etc. You are just doing a functional analysis or business analysis for your business stakeholders in your organization. So in those cases, the purpose of EDA is, or goal of EDA is going to be bring out insights through powerful visualizations, etc., powerful analysis, visualization, statistical techniques, etc. In other cases, you are going to use machine learning and deep learning. So in those cases, the purpose and goal of EDA are going to be to aid or help you pre-process the data or present the data in a format so that can be ingested by your predictive modeling algorithm, the machine learning algorithms or deep learning algorithms, etc., etc. The raw data that you receive from your business that needs to be used in the modeling process may not be in the right shape or form. So in those cases, EDA is going to help you in performing several analysis and being able to transform your data into the right shape and format. Okay, so in this diagram, they're going to be, I'm going to explain a little bit about where all, related to the previous slide itself, where all exploratory data analysis are used. Data exploration is a field where EDA is used extensively. So data exploration is used when you are doing functional modeling, business modeling, and early stages of your machine learning machine learning project or a deep learning project, etc. Going further on in your statistical learning and statistical analysis or your functional analysis or business analysis, you will also have stages of data cleaning. Okay, so data anomalies. So during those times, during those phases or steps, you will find a lot of data anomalies that you need to clean out or impute or kind of deal with. I mean, transform them in with different techniques. So data cleaning is another stage where you use EDA extensively, because you need to find out what are the anomalies that are existing. So you need to, let's say, find outliers in the data, in your numeric data that they're in your input data set, or you need to find out missing values in your data set, or there may be spaces existing in your data set where there should be numeric values, or there could be anomalous values present in your data set, etc., etc. So there can be different anomalies. There can be different needs for transformation of your data. So let's say your model can take data in certain units, and the raw data that you are receiving are not in those units, not in that format, and you need to perform certain data transformations. So those are going to come in data cleaning, and to bring them out in the open that will present the need of those data transformation and anomalies is going to be done through exploratory data analysis. Okay. Further on, this is more in a situation where you have a machine learning project going on, where you have to use predictive modeling, either prediction models like linear regression, etc., or classification model, let's say for instance random forest or decision trees, or for instance support vector machine, those kind of machine learning algorithms for classification problems, where there are model building or machine learning model building or deep learning model building is involved. You would use exploratory data analysis extensively for various purposes. One, for visualizing results coming out of those model, There are a lot of diagnostic that you may need to perform using those models. So let's say, for instance, one of the diagnostic that you may need to perform on your classification solutions or classification modeling is ROC curve. Okay, receiver operating operator characteristics. Okay, so ROC curve is drawn using visualization, and that is part of EDA. So for machine learning, deep learning case situations, there are a lot of diagnostic cases you need to perform using EDA. And when your modeling process is over, or your functional analysis or business analysis process is over, you have gone through the initial diagnostic, you have gone through data transformation, data cleaning, you have gone through modeling, you will need to present your final outcomes using charts and graphs. And there are strong techniques or libraries available throughout the data science spaces to perform those operations, creating charts and graphs and etc. There are Python libraries available if you are using R language. There are libraries available for R language. There are analytical tools available like MATLAB or Tableau, Power BI, K9, etc., etc. So there are tools and languages, libraries, plethora of opportunities available for performing exploratory data analysis. So these are some of the situations where you would and purpose and goals where you would use exploratory data analysis in data science and machine learning situations. Now, some of the types of EDAs or techniques of EDA techniques that are available in EDA are univariate analysis and multivariate analysis. I mean, univariate analysis are those analysis or those techniques that you apply on a single set of value. A single set of value is one feature or one attribute or one column or one field in your data set. Okay, so when you are performing an analysis which involves only one feature, it is called univariate analysis. And again, within univariate analysis, there are non-graphical techniques, maybe statistical techniques, and there are graphical techniques that are available. So let's say, for instance, this particular graph that you are seeing here, it is called a histogram, and histogram is an univariate. This particular histogram is an univariate analysis. Now, what do histograms reflect? Histograms reflect the counts in various ranges of your feature values. Okay, what does it mean? That let's say, for instance, in your data set, you have employee salaries. Okay, now in employee salaries, you have a population, a large population or the largest population which are in the salary bracket in this range, and there is a smaller population which are in the salary bracket in this range. Okay, very low salary, very few people, and gradually the population is going higher, and there is one population who get the whose number is the highest, and they are in the salary ranges of this. All right, and then there are people who are in higher or very high salary bracket. So let's say for this one, okay, so the top bosses in the organization who get very large salary packets, the number of that is very less. So this is one example of a histogram, which is essentially an univariate analysis. So essentially, in different brackets or different ranges of values in that particular feature or that particular field, what are the number of counts available in your data set? And this is also called a bell curve. So some of you may have heard of bell curve in kind of performance grading in your organizations. So this is actually called a bell curve or normal distribution. Okay, so if you get into statistical techniques, you will learn about various types of distribution, and this is one of the popular kind of distribution that we normally observe in our data. All right, so again, as I said, that univariate analysis, there are graphical and non-graphical techniques, and multivariate analysis, which also have graphical and non-graphical techniques. Now, what is multivariate? So let's say take an example of a bivariate analysis. So bivariate analysis is where through a graph or a chart, we actually reflect the relationship between multiple features. Okay, so the univariate one is analysis applied on, or statistical analysis or graphical analysis applied on one single feature, and bivariate analysis or multivariate analysis are those analysis or those visual techniques or non-visual techniques applied on multiple features or multiple variables simultaneously, more often to portray their relationships. So for instance, here in this particular graph, this is kind of is a combination. I can probably say it's a combination of univariate and bivariate analysis. Now this box plots show distribution, and distributions box plots show population distribution, which reflect almost the same information that are reflected by a histogram here. Okay, so for individual features, it's probably an univariate, you can say it's an univariate analysis. But again, if you think of it, say this data is about life expectancy values of population in countries in Asia, and this is a distribution of life expectancy values of countries in Europe, or this particular one is distribution of life expectancy values in Africa. So this is normally a bivariate analysis, but individually this box plots are also univariate analysis, but confined to only data within Asia. Okay, so in combination, this is a bivariate analysis where we show you the relationship between the life expectancy data in various continents. Say for instance, this particular bar graph is about in particular months how many units of goods that your company has sold. So this is the relationship. It's showing the relationship between the number of units sold against the dimension of month, okay, or date of sales, right? So this is again another example of bivariate or multivariate graphical analysis. So EDA, as you have seen, there are univariate analysis, and there are multivariate analysis, and graphical ways and non-graphical ways. And we will see some examples in terms of code as well. Now some of the graphs or charts types that we can use, and mostly done in multivariate graphical analysis. And I mean, most of the analysis or EDA that you will perform are going to be multivariate analysis. I mean, there are also important univariate analysis, but probably 10% of your entire EDA is going to be univariate analysis, and 80-90% of your EDA is going to be multivariate analysis, where you take in relationships between multiple variables or multiple features. So some of the techniques that we use are scatter plot. So this is one example of a scatter plot, so where you have plotted your data points along the x-axis and the y-axis, and each of these dots are your data points. Okay, so if a data value is has a Cartesian coordinate of say 1, 0.2, then this purple dot is your data point plotted over here. Okay, so based on the Cartesian values of your data point, or the value available in your data set, that can be plotted along the x-axis and y-axis, and this is called a two-dimensional surface. And on two-dimensional surface, you can plot relationship between two variables. Okay, not more than that. For projecting relationships between three variables, what you need is a three-dimensional surface. Okay, so you need a 3D graph. All right, and there are tools and techniques in almost every language and library, and tools like Tableau or Power BI or Keynote, etc., that give you the feature, or even Python, Matplotlib, or Seaborn or Bokeh. Those libraries give you the ability to draw three-dimensional plots as well. Okay, scatter plot in three-dimensional surface, or any other plot in three-dimensional surface. Okay, however, there are ways of plotting three-dimensional data in two-dimensional surface as well. If you look at this particular example of scatter plot, it is actually an example of plotting three dimensions on a two-dimensional surface. The third dimension is reflected not on the scale, the X scale or Y scale, but in terms of the color. So if you see, there is a color bar over here, and the third dimension is reflected or presented by the color of the dot. Okay, so there are various tricks that you can use in various charting. This is like a trend plot, and this is again, it's a time series plot. I mean, you can draw a stock market trend. You have stock prices along a series of dates and stock prices, and then you can plot them as a line plot like this. It's a trend plot or a line plot. This is something which is called a heat map. Heat map. We are going to in our coding we are going to look at a heat map. Heat maps essentially does what? They look at all the features of your input data set and create a plot like this, which is called a heat map, with the color scheme or projected values within the cells in the heat map. It conveys for every combination of features what is the degree of relationship. Okay, so within your input data set, if two features are correlated, that means, say, feature A or field A in your input data set moves at the same rate as feature B in your input data set, then these two fields are called correlated. Okay, so if those kind of relationships are present within your data set, that is not desirable for your predictive modeling or machine learning modeling. So in machine learning modeling, before machine learning modeling, you always have to perform a collinearity, multi-collinearity evaluation for your data set, and one of the means of performing that is using heat maps. And say for instance, this particular cell over here has 0.77. So when you have a value of 0.77, it reflects high degree of collinearity, and one of the variables in the combination has to be dropped. Okay, so those kind of EDA can be performed, right? So with that, we will go over to a coding example. All right, so we are going to start off with our coding example. So we will explain the problem statement first. So the problem statement is that Lending Club is a micro lending company in the US. So lending is like loans. So we are aware of home loans, we are aware of car loans, personal loans, etc., etc. This is kind of a personal loan, but the quantum of these loan values are very, very small. So let's say for instance, if you go to a bank with a loan requirement of 50,000 rupees, they are not going to entertain you, because it's too small to the smaller quantum compared to what they are used to. Okay, so they normally deal with larger value loans. So let's say you're buying a car, you ask a loan for 5 lakh rupees or 10 lakh rupees, so they are happy about that. But banks normally would not be interested in giving you a loan of 50,000 rupees. Now, who is interested about taking a 50,000 rupees loan? So let's say for instance, mom and pop store owner. So he or she doesn't have cash in hand at this moment to stock up the inventory at this moment. So his or her requirement, that the owner of a mom and pop store, a grocery store, a kirana store, is smaller. Okay, so in those cases, and also these guys sometimes do not have credit history also. So if they go to a bank or any other kind of organized sector, large financial institution, they are not going to be interested in giving them such small quantum of loans. So what is the alternative? Alternative is there are a lot of micro lending organizations that give out loans of this kind of quantum. They have other ways of checking your credit worthiness, and that's not part of the scope here today. But Lending Club is one such organization in the US, and they have faced a lot of issues with defaults. Default means people not paying back their mortgages or loans. Okay, so what they have decided to do is that they wanted to perform an exploratory data analysis on the transaction data that they have. So they have a lot of historical data. With that data, they want somebody to perform an exploratory data analysis to find out which of the parameters or which of the attributes of customers are more responsible or influencing the default behavior more. Okay, and this is one of the common examples for teaching exploratory data analysis, and we have decided to take the same example. However, this particular session is going to be short, and we will not have the opportunity of performing the entire analysis and making conclusions, solid conclusions out of our analysis. We are going to, the purpose of this session, the goal of this session is going to be showing you some techniques which are used in exploratory data analysis. Okay, so that is going to be our purpose. So let's see what are the steps that we perform. To start with, we are going to import all the libraries. So that is obviously a given. So if you have some basic knowledge about Python, these are the libraries that we commonly work on. NumPy library gives us the features to manage arrays. Pandas library gives us the features to manage data frames and series objects. Matplotlib and Seaborn are libraries which are used for visualization. So these are some of the libraries which are most used for our analysis, okay, for any exploratory data analysis, because arrays and data frame and series objects are very commonly used. The next thing that we do is import our data, which is in the form of a CSV file, comma separated value file. Import that using the pandas read CSV function into a data frame. So lone work is our data frame that we are going to work with. Okay, so this is what our data looks like. So in the initial data set, we have 39,717 rows, which is good news. I mean, for your data analysis, machine learning, deep learning tasks, as much data that you can have is better. And this is a large data set, so almost 40,000 rows of data or 40,000 observations. What is not so good news is that we have a lot of columns. So more than 100 columns, 111 columns. Now that makes the data very difficult to handle. So I mean, you can still possibly perform a lot of analysis even with this complex data with so many fields. But then, okay, so for learning's purpose, we will keep it simple. Now, when you visually inspect this file, you see there is a lot of data, I mean, a lot of features which are having missing values. So this NaNs are all missing values or null values. All right, so there are a lot of them, or there are certain fields which also have uniform values which do not have any significance. So we have done a visual inspection, and we are not going through the entire file. We don't have time here. So for utilizing our time better, so we just say that we have visually inspected this file. Normally you have to spend probably a few hours visually inspecting each of the fields during your analysis, initial analysis process, to find out which feature are worth retaining for your data analysis and which feature are not, because you have to you have more than 100 features. So even if you have to literally manually scan through all this, I mean, there is no automated way of finding those things out. There are some tools and techniques that you can use, but a lot of manual visual inspection is needed. Okay, so we decided that all these fields are not useful to us, and we have decided to drop them. So we have used the drop function, the data frame dot drop function, to drop these features. Okay, so these are some of the initial things that you do. So your number of columns have come down to 26. I mean, this is much more manageable than 111 fields, definitely. Okay, so make sure that you simplify your data set when you receive it at the first process after visually inspecting it. I mean, believe it or not, most of the organizations I have worked for, I have experience with, if you go to any functional department and ask for data, there are going to be a lot of junk data. I mean, realistically, every organization, every functional department carry a lot of junk data. So your data analysis will have to have that step of analyzing junk data and removing that junk from your data set. Second thing that we are doing is that there is this loan status field which is of a lot of importance to us, which tells us whether this person. So okay, so there are records of 39,717 persons in this data set, and this loan status field has a value, a possible value called charged off. If it is charged off, if the loan status value is charged off, that means this person has defaulted. Otherwise, he or she has not defaulted. So what we are going to do is that for numerical statistical analysis, we are going to transform the value of loan status and create a new field. I mean, not transform the value of loan status, but create a new field where we will put y1 if the value of loan status is charged off, otherwise 0. Okay, so that will tell us which of the customers have defaulted and which of the customers have not defaulted. We do that using the apply function and using a lambda function in between. So lambda function are very powerful, simple techniques of performing simple operation on a entire data set, and lambda functions are pretty fast as well in comparison to normal iteration operations. And you should actually learn about lambda function and how they work. So essentially what happens is that x translates to, I mean, lambda functions are anonymous functions. So normally if you talk about functions, you think about named functions, and lambda functions are not named functions, they are anonymous functions. They can take multiple input parameters, but they return one value, and they only have one expression. Okay, they cannot include multiple expressions in themselves. Okay, so the x is translated from, or x is resolved, which is the parameter. X is the parameter, input parameter of this lambda function. So x is the input parameter to our lambda function, and x is coming from the loan status field from the loan data frame, our input data frame. Okay, now what happens is that we see that there is no iteration applied. However, we have 40,000 rows in our data set. So what will happen is that this lambda function in this case is going to, because of the apply function, the lambda function is going to get executed iteratively for this many number of times as there are values in here, and for each iteration the subsequent value of loan status feature is going to be passed on to x, and it is going to return 1 if the value of that parameter is charged off. So that means the value of loan status is charged off in that particular iteration, is going to return 1, and otherwise it is going to return 0. So the value that is getting returned from lambda function in each of the 39,000 iterations, the value is going to the new feature in the loan data frame called defaulted, and that is what we wanted. Okay, so if you kind of display the value of defaulted, they look like this. So this particular one or this one mean that for this customers the loan status was defaulted, or sorry, charged off. Okay, that means defaulted. Okay, so with this we move on to the next one. So this is the describe is a function which kind of show you the statistical information about the numeric fields from your input data sets, which is loan, which is a data frame. So it shows you the count and the mean, the standard deviation, the minimum value, the maximum value, and the quartiles, which is 25th quartile, 58th quartile, and 75th quartile. Now just note the fact that describe returns the statistical information, and the statistical information is only relevant if your data is numeric. Okay, so describe smartly picks up all the numeric fields. It does not touch the, or it does not analyze the textual values or other values, right? Okay, so here is an analysis that you can do, that you can see what is the mean and whether they are in your expected ranges, or you have mean value and the quartile. So this is 0th quartile and this is 100th quartile. Mean is 0th quartile and max is 100th quartile. And looking at each of these values for these fields, you can actually ascertain, okay, is there any outlier? Are there anomalies between the spread of values in this feature between the mean and the 25th quartile and the 58th quartile? So if there are smooth transitions through these quartiles, then your data is looking good. Otherwise, there may be issues of outliers. So in case of outliers, if you figure out there could be outliers in this in your features from what describe returns, then you may be able to, you should be performing further analysis using techniques like box plot. Okay, Seaborn or Matplotlib both will provide you with options of drawing box plots for features. Okay, now there is another function called info in Python that's actually part of the pandas library, which gives you this information, which is the list of columns, and for each feature or each column in the data frame, the number of not null counts in that. So what is the count that is desired in this field is one that is equal to the number of rows. So if this value is equal to the number of rows, that means that there are no null values in that column. Okay, so here is one example where it is not equal to the number of rows. The number of rows is 39,717. It is 37,258. So the difference, which is 39,717 minus 37258, is the number of missing values or non values that are present in this feature. And why do you need this information? You need this information because null values are something that your modeling cannot take up. Machine learning algorithms may not be able to take up, and you need to do something with those null values. So either you need to impute these null values with a desired value, either 0 or 1 or the mean of that particular feature, or there are different techniques, but the technique has to be relevant to the particular business problem that you are dealing with, the particular business data that you are dealing with. Okay, or there could be other options or techniques like dropping the rows which contain the null values, and that may be the safest option, but you have to consider cases where if you're if there are null values in lots of observations, and that's a big percentage of your input data set, then dropping those many number of rows is going to be troublesome for you. So in those cases, you probably have to look for other methods of dealing with the null values. Okay, now I want an analysis of I want distribution. There are two features called loan amount and funded amount, and I want the distribution of loan amount values and funded amount values side by side, so that in terms of bar chart, so that I can compare them. And I also understand the distribution of this two fields. So let's look at the loan amount first. So this is a histogram, and we explained the histogram in our the PPT that I was going through. And histograms are methods of portraying the distribution of the data. So what that means is for the loan amount, for loan amounts between, say, this is the scale between 0 to 5,000. So this particular scale is like say 1,000 or 500 to 3,000 or 5,000, 500 to 2,500. For this particular range, the number of counts of loans that are disbursed in that particular range, or rather not disbursed, applied for, because loan amount is applied for, funded amount is disbursed amount. Okay, so number of loans that were applied for is this, right? So which is around a little above 5,000 it looks like. and the funded amount for that particular range is a little above that. Now that is a little strange, because normally your disbursed amount, I mean, there could be different other business interpretation as far as lending club is concerned, but normally what I would think is that the disbursed amount or the funded amount here is always going to be, or almost always going to be, lesser than the loan amount. So there could be other explanations which I do not know. Okay, so similarly for this particular bracket, these are the number of cases where the loan amounts are in this bracket, and the similar number of counts for the same range of funded amounts as well. Okay, a little above that, little above loan amount. However, as you go towards the right, and the loan amounts tend to get larger and larger starting from this particular range, you see that the funded amounts get smaller than the loan amount. Okay, which makes sense, which is okay. All right, so this is how you can look at distribution. So in isolation, loan amount distribution and funded amount distribution, and you are also getting a comparison. So this is a kind of univariate analysis, you can say. Now the same thing you can perform through a box plot as well. So this particular box plot, which is drawn on the loan amount only. So previously we got a comparison between the loan amount as well as funded amount, but in this particular case we are drawing a box plot only for the loan amount. Okay, so if you see that the largest concentration, so this is your minimum, and this is your kind of maximum values, and these are outliers, and this is between your 25th quartile to your 75th quartile. Okay, so this is 100th quartile, and this is the median value, right? So this is the largest concentration. So the largest concentration is between around 5,000 to 15,000. So that is what the box plot conveys. Okay, so this is also another way of plotting distributions of a specific field, which is in our case loan amount, but the box plot also shows you the concentration of the outliers. This is a single distribution histogram distribution of loan amount, which is same as this one. I mean, this is done in a slightly different way with two separate fields, and this is only a single field. Okay, this is also done through the hist function of matplotlib. Right, now we want to look at the quartile. So I mean, this is demonstration. I mean, this information you have already got through the describe function above, but just in case you want to extract this information from a single specific field, you can do that using this function. So you want the 25th, 58th, 75th and 100th quartiles of 100th quartile is your max value of annual income and you can actually do that using the quartile function, passing the parameter which is q equals to, so you have to mention which quartile is that. So q equals to 0.25 is going to give you the return you the value which is at the 25th quartile for this particular field, which is annual income. Okay, same you extract the value for annual income's 50th quartile value, 75th quartile value and so on. Okay, and if you want to extract the median value of annual income, you can use the median function for that. So describe gives you the same information, but just that if you want to use the get the same information, extract same information in terms of individual values, you can use these functions. Right, then we draw a distribution for annual income. Now this is a bummer because there are so many outliers that the box plot is not understandable at all. Okay, so the actual distribution, which is the box plot here, is not understandable at all because the outliers are stretching the x-axis so much. Okay, so what is the remedy to get around this problem? Outliers normally have a very small percentage. So what I have decided is that I will extract only 99% of the data, or bottom 99% of annual income, because the top ones are the outliers. And if I just extract the top 99%, then my box plot is going to be much more understandable. And I do that here is I find out the number of entries which are going to be 99%. So basically, basically the total number of observations that we have in our in the annual income field. So we can also take the number of observations that we have in our data frame, but it is better to apply the count function on the annual income field, because if you take the total number of observation instead of count of annual income, they may be different in case there are a lot of missing values in annual income. Okay, which is not the case in our case from our from the output of the info function on the data frame. But it is better, always better, to apply the count function and get the total number of counts in that particular field. So total is going to give you the 99% number of the total number of values that are there in annual income. We are going to create a new data frame for our purpose, which will have two fields. One is defaulted and one is annual income. And then we are going to take that and sort it on annual income field. Okay, sort values, right? And the sorting is going to be in the ascending order. Okay, the lowest values first and the highest values at the end. Now if you want to do the reverse, you have to add a parameter called ascending equals false. Okay, so that is going to reverse the sort values order. Now in this case we want the sorting to happen in ascending order. Why? Because we are going to use the hit function, and the value of total is the 99% count of the total number of counts in the annual income field. Okay, so what it is going to do is it is going to slice off the highest 1% from this data frame. Okay, and display that and take that into lone temp. Okay, so now that we have chopped off the 1% outlier from the top, we draw this, which is a box plot of the defaulted feature and the annual income feature. So defaulted feature is along the x-axis, and what are the possible values of defaulted? 0 and 1. 1 means this person has defaulted, 0 means this person has not defaulted, and annual income. Okay, so this is the distribution. Now why were we interested in finding out the relationship between defaulted and annual income, and that is to the spread? Because we wanted to see if people with higher annual income default more or lower annual income default more. And similarly, whether yeah, so this is the default one. So we wanted to see if there is any relation between annual income and default propensity. So essentially, okay, so there could be a perception that you can take that, okay, people with lower annual income default more, which is probably not the case here. That the median of the distribution of the default population or defaulted population is definitely lower than, in terms of annual income, the non-defaulted ones, but there is not too much of a difference. Okay, so if we thought that people with lower annual income would have defaulted more, that is probably not true from this distribution. Okay, so this is another analysis that we have done. Okay, just to be sure, right? And then we are going to do a univariate analysis on interest rate, quantitative interest rate variables. We are going to do the same thing that we have done in the previous example with annual income and try to find out if there is any influence of annual income in the defaulted rate or not, which we kind of concluded that there is not much of a difference. I mean, not much of an influence on of the annual income field or annual income value on people's propensity to default or not return back their loaned money or lent money. Loaned money. So in this case, what we are going to be interested in the same analysis on interest rate. So we are going to try to find out whether, and these are the questions that you have to continuously keep asking on your data and try to find the answer using this analysis, using this visualization. So another question that I am asking, is there any influence of the interest rate on people's propensity to default? So that means, is it that if the interest rate of the loan is higher, then people default more? And that particular question is probably an yes. So in your default population, you see that the median value and the distribution, that the 25th quartile and the 50th quartile, all of these are higher in case of the interest rate. So the median non-default interest rate is about 11%, and the median defaulted population interest rate is about 13%, 13.5%. Okay, there is a significant difference, right? So this is kind of a story that tells us, okay, I mean, this is the answer that tells us that, okay, if the interest rate is higher, then people tend to default more. And this is the univariate analysis on the interest rate. So basically, these spikes are the number of counts of loans of that are given out in this interest ranges. So again, I mean, the most number of loans are probably given out in this interest range, so which is about 13 or 14%. Similarly, equal number of loans are given out in the interest range of about 10-11%. Similarly, loans are given out more in the interest ranges of about 7% here. Okay, if you look at the scale, so that is what it turns out to be. All right, so we just need to investigate as to why there are these spikes at these particular ranges. So there is a spike here, there is a spike here, there is a spike here. So there must be some explanation about these spikes in this particular interest rate ranges, because at these interest rates the loans given out are much more. Okay, and there could be certain relationship between those spikes and default rate as well. Okay, so there are further investigations that we need to perform. Not all of these investigations are part of this particular session, but these are the analysis that you need to perform. And again, I'm not getting too much into the code, but you can get into the code and stop the video, get into the code and understand the syntaxes and the kind of commands that are used. Okay, now there is a field called loan status. Now if you remember, we have used this loan status field, and we have created the defaulted new feature called defaulted, and we have said that when the loan status value was charged off, set the defaulted feature value as 1, and for all of the others set it as 0. So fully paid and current are set as 0 and charged off are set as. But now in this case, what we do is we do an analysis as to how many of the occurrences or how many observations or how many customers in our data set are fully paid and charged off as comparison to the current one. So I mean, these are the active loans at this moment. That's what I can make out. Okay, now plotting this bar chart is fairly simple. So what you do is you do a count plot, a seaborn count plot, which is a bar plot. And what you do is you take the loan status field from the loan data frame. So pretty simple explanation or pretty simple syntax, and that has created this bar plot, and what it tells you is that okay, 32,950 and 80, which is 83% of the total population of the data set, are fully paid. 5,627 occurrences, 14% of the population are charged off. So which is, I mean, 14% charged off is a fairly high default rate, and there are currently 1,140 that are available. Now there is, I said, this part is pretty simple. Drawing the bar graph is pretty simple. So why is this too many complicated pieces of code here? So these are not complicated pieces of code. These are for setting the titles, which are the loan status, the y-axis title, and the loan axis x-axis title. So which is okay. Now this particular set of code is for generating these values. Okay, so what we wanted to have along with this bar is the number of occurrences this particular bar is reflecting. You can get an estimation from the scale, the y-axis scale, but I wanted a exact value and the exact percentage of it is of the total population. Okay, so to do that, we are not going to get into the full explanation of this code. So you need to do a little bit of study and understand. However, what we are trying to do here is that we have an axis object that is returned by your count plot, which is the bar plot, okay, which has plotted the bars. Okay, so this axis object is the basis or the foundation of our chart here. Okay, bar chart or bar plot. Now anything that has to be done on this particular chart has to be on the using the axis object. Okay, so this text that we are talking about here has to be using the axis object, and we need to tell the axis object, I want this text to be at a location which is on an x-axis offset by this particular margin, and on y-axis this particular margin. Okay, this particular text has absolutely no relation to the bar plot that you have already plotted. Hence you have to pinpoint the location, and that is what you are doing here. Okay, so axis.text is the function that we are using to print this data, the number of occurrences and the percentage, and these two values are the magnitude along the x-axis and the magnitude along the y-axis that you have to mention to pinpoint the position at which this text has to be printed. And this text is generated, which is this one or this one, using this command. Essentially you have calculated separately the number of observations and the percentage value. Okay, so rest is upon you. You can stop the video at any point of time. The recording is going to be available in YouTube, and you will be you can use that video. Okay, so the recording is probably going to be available sometime tomorrow, by tomorrow evening. Okay, so going forward, then we come to heat maps. So I mean, heat maps are an interesting representation of data in terms of feature correlation. So what we said while we were going through the slides is that in machine learning or data science or in predictive modeling, when you are using machine learning algorithms, one of the things that you need to figure out and weed out from your data is multicollinearity. Multicollinearity meaning that there are possible correlations between your data, between multiple features in your data. Okay, now how do I find that out? There is an easy way of doing it. Use a data frame, I mean the entire data frame, so that this takes all the features, and it takes only the numeric features. I mean, like say for instance describe picks up only the numeric features. So core function also picks up the numeric features, okay, because it cannot possibly find out correlation between textual features. So what core does is that it finds out, looks at each feature pair, goes through its values, all the observations, and finds out whether or not these two features have correlations. Okay, whether it's a strong correlation, weak correlation, no correlation, etc., etc. A correlation value can be between -1 and +1. 0 means no correlation, -1 means very strong or perfect negative correlation. So if you increase the value of one feature by 1, the other value decreases by -1. So it's a very strong negative correlation. And it can also be 1, which is if you increase the value of one variable in that feature in that feature pair, the other value also goes up by 1. So it's perfectly strong, perfect correlation. I mean positive correlation. Okay. Now anything else is between 1 and 0 or 0 and -1. So these are these values are called correlation coefficient, and each of these cells signify the degree or extent of correlation that this feature pairs has. So let's say installment and funded amount INV have a correlation of 0.9, which is very, very high. Okay, so definitely if you are going to do machine learning modeling, this one of the features in this pair has to go out, because you cannot allow multicollinearity or correlations among the data. Now when you have lots of fields, it's going through this whole matrix is very, very difficult. I mean, this is also, I mean, chord is also this one is also a data frame. Okay, it's the result is stored in the form of a data frame. So what is a better thing to do is creating a visualization, and which is the heat map. So this matrix here is transformed into this heat map, which is visually much more appealing and much more intuitive. And what you have to be bothered about is this values, or these values, where you have the dark ones, the extremely dark ones are strongly positive correlations. So these dark pairs are what you have to be concerned about. So let's say installment and this one here is very dark. So installment and the funded amount. Okay, and also similarly installment and funded amount INV. Okay, so these dark pairs are something that you need to be worried about in case you are doing predictive modeling. Okay, info function is one way we have found out which of the fields have null values, but there is another direct way of doing it. Use the data frame name isNow function, and sum of it is going to give you the number of null values existing in each of these features. Okay, so obviously imp title, imp length, they have large number of rows with missing values, and this one also, pub break, bankruptcies, a lot of missing values. You can also do a little bit of tweak if you are interested in finding out the percentage of null values in features. You have this code, you create a data frame with a column called percentage of null values, and make a calculation to find out the total percentage. So this particular expression is going to give you the feature wise sums of null values, and divide it by count, and multiply that by 100, and it is going to give you the percentage values. And you extract only those ones with a 0.05, I mean greater than 0.05 condition, and those are the ones that are coming up here. So this one feature, imp title feature, has 6.1% of or 6.2% of null values. Okay, which is a significant percentage, and you have to deal with that. Okay, we will skip this, pretty simple. Okay, now there is another interesting example that we are going to look at, is that in your imp title field, what we have here is the company that you work for, the company that the borrower works for. So UPS or Walmart, and retired or Internal Revenue Service, United States Postal Service, US Bank, etc., etc. And we want to find out, is there a propensity of people from a particular company or particular set of companies to default more. Okay, so let's say for instance people from Walmart, I mean it's just fictitious example that I'm taking. People from Walmart probably have come to know about a trick, and they are defaulting more. So those kind of percentages, I mean those kind of information that we need, and find out, is there more propensity for certain companies, people from certain companies to default more. Okay, so that's the analysis that we are doing, and what we are doing is that we are taking our data frame and we are grouping the data by imp title. So we are grouping the data by imp title, and we are taking the default count, and subsequently we are creating a couple of fields called okay, so then what we are doing is this: we are taking the count here and we are taking the sum here. So sum is actually returning us the values in the defaulted column, and totals is coming from the number of counts of applicants or loan takers from these companies in each of the groups that you have created. Okay, and when you have the defaulted and the totals from the count and sum on your defaulted column, after grouping them by imp title, you can also extract the default ratio. Okay, so we are creating the default ratio. So essentially you divide the defaulted number divided by totals, and you get the default ratio, and these are the default ratio. And the last thing that you do is organize this data frame in a sorted manner on default ratio. Okay, so the highest default ratio to the top. All right, and we see that they're about 26% default ratio, 27% default ratio from people from UPS, and it's a significant number. 25% people from Walmart is a significant number, are defaulting, etc., etc. Okay, so all right, I mean these are fictitious data, nothing to do with UPS or Walmart here, but these are the kind of analysis the company is going to be, or lending club is going to be interested upon. All right, so that one was interesting. Next we are going to see if there is any influence of the loan grade. So every loan is graded by lending club, and they assign a grade number, which is A, B, C, D, E, F, G, to the loan grades, and we want to be sure that there is any propensity of more defaults in particular grades. Okay, so if in a particular grade the number of, or the ratio of defaults are more than other grades, loans of other grades, then we need to be cautious about, I mean we need to inform lending club that, okay boss, your grade D has more propensity of defaults. Okay, and we need to do that here, right? So here is an interesting function that is offered by pandas that are making it possible. I mean there are other ways of doing it, but crosstab is a very interesting function. So first of all, we have these two fields, one is grade and one is defaulted. Okay, how many observations do we have? 37,000. all right, so there are 37,000 grades and then 37,000 defaulted counts, and we want a bar chart like this where we have the default counts, sorry, the non-default counts and the default counts in each of these groupings. Okay, what we are going to do is that we are going to show you how what the crosstab does. Now crosstab, I have just taken this expression, okay, and displayed here as to what crosstab does. So we have taken this two fields from the loan data frame and applied the crosstab function on it. What it has done is it has created a resultant data frame with two fields, and the two fields are the possible values of the second parameter that we have passed. Okay, and the rows are the possible values of the first field that we have passed, or the first parameter we have passed to the crosstab function. Okay, and in intersection of each of them it has plotted the counts. Okay, grade A number of non-defaults is 94,083. Now if you didn't use crosstab, you would have had to do some kind of group by and counting and etc, complex expression to find out this data. All right, but the cross-step function has made it easy. So at each cell, so let's say for instance for grade C loans, the number of non-defaults is 67,551 and the number of defaults is 1347. Okay, very interesting, very powerful function by pandas, and this is the data that we get, and we apply a plot function which is going to give us this bar chart. Okay, we pass this kind equals to bar and it plots this bar chart, right? Okay, so what do we make out of this data? We make out that none of these loan grades have a significant ratio of defaults and non-defaults. Okay, so we are good here. There is a field called DTI, and of course there are values of DTI. There are various values of DTI. You can go back into the input dataset and see the possible values of DTI. Apparently the values are in the range of 0 and say 24, 25, something like that. Okay, now what we want to see is if there is any influence of the DTI value on the propensity of default. And the way we want it is that if you go back, we have loan grades. Okay, now these are categorical values. Okay, so A, B, C and D, etc. These are categorical values, right? When we have category, for each of the categories we have been able to find out the counts of defaults and non-defaults. However, DTI is a continuous value, and to perform an analysis like this continuous value in DTI field has to be converted into a categorical value, okay, which is called bin, or bins are actually ranges. Okay, so what we'll do is that for values of DTI between 0 and 8, we will say we will have a new field and we will put 0 to 0-8%. When the DTI value is between 8 and 16, we will say 8 to 16% in the new field DTIT. And similarly between 16 and 24% and greater than 22. Okay, I mean this is a slight mistake. Greater than 22, but should have been this should have been greater than 24 because this is a range. All right, so slight issue in the code, but nevertheless doesn't hamper our purpose. So what we are going to do is that we are going to create this bins, and these bins are going to be stored. The bin values of DTI field are going to be stored in the new field called DTIT. Okay, so after for this for binning exercise, we create this user defined function called bin DTI, and we use the apply function and apply the user defined function on the DTI field here, and the return values are going to get into the new field. Okay, so when we display the values, this is what it looks like. Okay, so the DTIT new feature contains values like this. All right, so now these are your categorical variables. So the previous operation, your categorical variable was the grade, loan grade. Okay, and here now you have created this categorical variables in the new feature called DTIT, and that those categories correspond to the numeric variables or numeric values of DTI. Okay, now we perform the same operation as you have done with grading, but this time your categorical feature is DTIT. Okay, and this gives you this diagram or this bar chart. Okay, so now you analyze that if DTI values are between 0 to 8%, this is the ratio between non-defaults and defaults. If it is 16 to 24%, this is what it is, and between this, yeah, in comparison to this one, the DTI ratio for this particular range looks a bit more, on the side of defaults. Okay, so this is something that lending club may need to investigate, why there is a difference between 8 to 16% and 16 to 20%. All right, sorry, this yeah, 18 to 16% and 16 to 24%. All right, maybe homework for home for all of you is going to be, this is when you create this bar chart, it's not in sorted order. Okay, so 0.8% is coming here, and after that 16 to 24%, 24%, and then 8 to 16%. So what you can take home as an exercise is that how do we create this bar chart with the same information but in a sorted manner of the DTI ranges. Bivariate analysis on the purpose of loan against the charge of proportion. So this is pretty much similar to this operation that we have done, which is here on the default ratio per company. So again, charge of proportion is your default rate. What you have in your loan data frame is the purpose. The purpose feature has this possible values: small business, renewable energy, educational, moving, house, medical, etc., etc. There can be different purpose of so I mean, basically the purpose is lending clubs capturing of the reason why the loan is taken by the applicant, the borrower. Okay, now we want to be sure, what we want to find out is that for each of the purpose values, what is the charge of proportion or the default proportion. Okay, and what is the charge of proportion? The charge of proportion is the value which is the ratio between the total of this feature, or for this particular possible value of purpose, the total, the ratio of total and charged off. So 475 for small business, it is a value that is 475 divided by 1828. Okay, so what you need to do is, first of all, you need to group by the data on purpose and loan status. Okay, once that is done, you also find out the total by the counts of the charged offs, the current and the fully paid. Okay, and calculate the charged off proportion field by dividing the value from charged off and the total values for each of the possible values of purpose. Okay, so the first thing that you do is create this data, and you can look at the unstack, the expression that we have used. Okay, so this one here. All right, so the group by, so we go back to, while preparing the data, we have used this expression, all right, for creating this data. Now the first thing that you have done is you have grouped the data by purpose and loan status. So when you and you have taken the counts, okay, for each of the possible values of loan status. So when you do that, this is what you get, right? Now this is not helpful for you for creating this data. Okay, you want this values here, and you want this charged off, current and fully paid, and the counts against them as columns in this data frame. Now to do that, what you have to do is unstack, and if you unstack, this flips this structure. The unstack command or the unstack function flips this structure against each of the group by values. Okay, so if I run this, you see what happens. So the possible, the counts of every possible values of purpose in terms of their charged off counts, current counts and fully paid counts are structured like this. Okay, so first it was a group by structure, and now this is a unstacked structure. So once you have the unstacked structure, which is in the form of a data frame, you carry on with the subsequent commands like this, okay, to find out the charge of proportion. Because if you have got the charge of counts and the current counts and the fully paid counts, and then you have counted the total, which is the sum of all these three, then you can calculate the charge of proportion. Now in the unstacked manner, you can derive the total and then charge of proportion quite easily. So your purpose was group by and then getting this three fields, which was possible through the unstack function. Okay, so powerful and interesting command. And then what we wanted to do is compare the distribution, or compare the proportion of charged off against each purpose of loans. All right, so and this is the bar plot. So you see the propensity of defaulting for loans taken for small businesses are the highest, followed by renewable energy and educational purposes. All right, so now we have got some clue as to what are the different reasons people can default. All right, with this example, we will stop or finish this session. Thank you for joining this session from TechSands, and we hope to see you again.